All right, so today we're going to discuss Chapter 10 of the textbook. And it's an interesting chapter. Um, a lot of what they, there's some philosophy in their chapter, as much of which I take some, not umbrage, but certainly disagree with. And we'll hopefully we can discuss some of those things as we go along.
I've
So
never
the
seen
textbook,
Umbridge before, but if you want to give us a demonstration sometime, I'd appreciate it.
Umbridge. She was in Harry Potter, I think, Professor Umbridge. But anyway, oops. So the textbook breaks the chapter down into these seven categories, and so we'll go through those. Although they have a section on adjusting the net zero timeline, which I'm not going to discuss today, which is perhaps the section I take the most umbrage to. And if anybody would like to discuss that with me, I'd be open to that at a later date. Okay, so the first thing they talk about is increasing metal demand. And they note that there's increasing attention on the issue of sourcing critical metals as we transition from fossil fuel to perhaps a green economy or to net zero, depending on how you like to frame it. Bob and I were talking about this yesterday, and maybe net zero is a much longer term exercise, but certainly we can move to a greener economy, less reliant on fossil fuels. And so they also note that predictions of future critical metal needs are highly variable and subject to change. So, for example, some estimates of the needs for increase in lithium are 1,000% increase over the next 30 years, but that sort of ignores that there's new battery technologies that are coming online. And implicit in this is, which they discuss, is population growth. And so the plot on the diagram in green is the increase in population, and we've now passed 8 billion. And I think we passed 8 billion in 2024, I forget. And then the purple line is the population growth rate. So you can see by 2100 there'll be 11 billion people, according to this estimate, which is a UN estimate. But the growth rate will be down to 0.1%, which is well below replacement level. So things will flatten off and then, I guess, decline. But the point is that we have a growing population, so we'll need more metals. And with a greener economy, we'll need more critical metals. And the image there is just sodium-ion batteries are becoming are gaining more attention. In fact, I think in China they're actually utilizing sodium-ion batteries as a replacement to lithium-ion batteries. And people argue that they're a lot safer. They don't combust the way lithium does. They can operate at a wide range of temperatures and so on and so forth, and are cheaper because sodium is far more available than lithium. So the textbook, so I've got, throughout the lecture, I've got some direct quotes from the textbook. So this quote is, "This is not the place to discuss the geological factors related to long-term climate change that are also largely ignored by the media and others." So I wanted to ask the question, do people feel that the media ignores geological history and the fact that the climate has changed over geological history? What are people's thoughts on that? If anybody's thought about it.
I would agree that the media ignores it. I don't actually see it as a problem though, because I don't think people can really comprehend geologic time for the most part. And then the other part of it doesn't really matter what the Earth has been in the past. Like, no matter what, the Earth will be fine. When we're talking about climate change, we're really talking about the consequences for humans. And even if these were temperatures or like climate periods experienced by the Earth, humans did not experience them. And so that's where, to me, the distinction comes in.
I completely agree. Yeah, good, excellent point. Anybody else? Okay, well, I'll move on then. So they also said that all estimations of future demand for metals, particularly critical metals, can only be indicative, not predictive. And so despite uncertainties, there are clear indications that increasing production of critical metals will be required to fuel net zero expectations. And I think that we could all agree that that's true, that as we transition to a much greener economy, it's clear that the need for critical metals will increase. And so they have this chart here. So just listing some key critical metals, and where they're going to be needed. And the ones in yellow are where there's been relatively little previous mining for those commodities. And so, and they're mostly trace. In other words, they don't typically form deposits of their own, although lithium does. But and so anyway, it's just a chart showing where a lot of these critical metals will be used. So they discuss that there are serious concerns as to the future supply of critical metals as we transition to a more green economy. So they quote, climate change and attendant net zero policies are placing increased pressure on declining global metal reserves and resources. And so what about recycling? You know, they do note that, and I found this really interesting, that over 90% of aluminum is recycled. And they note that 75% of aluminum ever produced is still being used, which just blows my mind. When you think of the size of landfills and things like that, it's almost an unbelievable statistic, but it's in the book. Anybody have any comments on that? That's really amazing to me.
I just wonder what it would take to get that for a lot of the other critical minerals we have, metals.
Yeah, well, certainly steel is heavily recycled, and as I think I have in another slide, copper, about 30% of the copper is recycled. So anyway, the authors state that many commodities will be exhausted before 2060 without major new discoveries, and so we could discuss if that's true, right? And in my view, this is the economics of metal extraction, which we have talked before in previous lectures, but that will also change. So if the major resources get exhausted, then there's lots of materials that have much lower concentrations, which might become economically viable to extract, as if we ran out of primary resources. At least that's my take on it.
Well, another thing about aluminum is it's easy to recycle because aluminum can, right? In some localities, you pay a deposit on it and you get that back if you return it. Even in places where you don't, you can still turn in aluminum cans for money, and you see the homeless doing that. You know,
Yeah.
This is one of the interesting sort of sub-economies that exists because aluminum is so it's basically not it's often in a product by itself. That's what I meant to say.
Yeah.
And that makes
Yes.
it really easy. Plastics, that's a really different problem, right? We're not talking about plastics, but people recycle their plastics, but at least the last time I looked, those plastics are not recycled. There are very few of them compared to aluminum.
Yes, very small proportions actually recycled, because there's so many different kinds of plastic, whereas there's only aluminum is aluminum. Well, actually, there's two kinds of aluminum. In England and New Zealand, it's aluminium, but you know. Okay, so the issue of scarce critical mineral resources could be met with new discoveries and increased exploration. And the authors note that there's the number of issues regarding this. So one is environmental awareness. And so as we become more aware of the impact of mining on the environment, and I guess we could argue that if mining companies paid more attention to it, not that they don't, but if they paid more attention to it, maybe there'd be less resistance. But the very large Windy Craggy deposit in British Columbia, it's a very large VMS, one of the largest in the world. And unlikely to ever be mined because it's in a national park now. And then the Pebble deposit, which is a large porphyry copper deposit in Alaska, is also unlikely to be mined because of concerns to the local fishing and First Nations communities. So decreasing grades. So global average copper grades have progressively declined from over 8% in 1970 to just over half of 8% in 2020. So that's a significant decrease in the average copper grade being mined. They also note the lack of geoscience expertise at the top of major mining companies. And so, the major mining companies aren't necessarily all that interested in greenfields exploration, but more the acquisition of properties that other people find. And then we have to find ever deeper deposits because a lot of the surface or near surface deposits have been found because they're easy to find, relatively speaking. So this is just part of the table they have in the text. It's quite a dense table. And so I just wanted to, if we just run along the top, so for the Pebble deposit, you can see its grade is half of 8%. It's a very large deposit, 36 million tons. But the color code here is related to risk, from high to moderate to low risk. And so you can go across and say, well, the grade is only a moderate risk. It's low grade, but there's lots of it. There's lots of water available, so it's a relatively low risk for the water, relatively low risk for the tailings. Grade variability might be a higher risk. Legal is a much higher risk because, again, of opposition from the local community, so that's also relatively high risk, and so on and so forth. Whereas for other deposits, you can see the next one down, the Kamoa-Kakula, is very high, very rich deposit, 2.62 equivalent grade of copper. It's very large. So its grade is low risk, but water usage, permitting, and so forth, and poverty in the local communities, although I'm not sure I quite understand that one, and impacts on biodiversity are high risk. So I'm not going to go through this exhaustively, but it's an interesting table. Okay, so the number of discoveries versus expenditures. So the red line is how much money gets spent on exploration, and the drop off is partly related to there was a sort of a mini economic crash in the mid 2010s, and then we got COVID, so the expenditures decreased. But the blue bars represent the number of discoveries, and so there's an apparent decrease in the number of discoveries despite increasing expenditures in mineral exploration. That's for all commodities. So, that's partly reflected in the fact that most near surface deposits have probably been found. And then if we look just for copper, so this is again the same kind of chart. So copper exploration budgets versus copper discoveries, and the lighter shade of turquoise is the projected new copper in major discoveries. So in other words, those are deposits that haven't really been assessed for their true resource. So this is an interesting chart. So this covers a bunch of commodities. So in the upper panel, it just shows the number of deposits that are found for gold, base metals, uranium, diamonds, iron ore, coal, and other. And again, you can see that we increased in discoveries up until the 2010 or so, and then things have dropped off since then. And then the bottom plot is just the proportion. So what's interesting about this is that gold and base metal deposits make up the bulk of discoveries. This is a similar chart, but it just shows what jurisdiction is doing the discovering. And so you can see it, if we just look at the percentage share, we can see Australia has increased from very little in the previous parts of the last century to a significant share now. Africa is significant, and China has become increasingly significant. And I don't think, oh, there's Canada. Canada's still in there. In the USA, I guess there's a slight increase lately, presumably because of gold in Nevada and things like that. And so this figure just shows the depth beneath cover on the y-axis versus time for gold, base metals, uranium, and then precious commodities like diamonds, PGE, and silver. And really the take-home message here is that through time, on average, deposits of discoveries are getting deeper and deeper, with the notable exception here of gold in South Africa. So the deepest mines in the world are gold mines in South Africa, going incredibly deep, more than 3 kilometers here. And so this is the way that deposits are found. So project scale means at the staking a claim scale, and prospect scale means at drilling a target scale. And so it's through time. And it's kind of interesting. So in the early days, prospectors found most of the deposits. Now, most deposits are actually found around other deposits. That's this big sort of pale orange color. And so, you know, the easiest place to find mineralization is around mineralization, is the take home there. It's nice to see geochemistry becoming increasingly important, and then there's geophysics and things like that. And this is the depth through time. So again, project and prospect scale, so staking versus drilling. And again, you can see that as we go deeper and deeper, the proportion of deposits found around other deposits is dominant. Okay, long quote from the textbook. So given all these expertise, funding, organizational, and land access constraints combined with hard evidence for discovery slowdown, it seems highly unlikely that mineral exploration alone can meet either short or long-term global critical metal demands if the drive toward net zero in 2050 or 2060 persists at projected future rates using clean energy driven by critical metal technologies. So it sounds to me like the Muller et al. Are skeptical that we're going to be able to produce enough critical metals to meet the demand if we continue our drive to net zero. They then discuss deep sea mineral deposits, which we're going to talk about later today, particularly manganese nodules represent an attractive potential future metal source. However, access and exploitation of these metal resources on the seafloor will require the introduction of contentious marine mining legislation and resolution of perceived environmental issues. So they're perceived environmental issues. I think there are real environmental issues associated with deep sea mining. It's a question of how important they are versus the return in terms of metal resources. So then they continue, hence these resources are unlikely to resolve critical metal shortfalls even in the longer term. Does anybody have any thoughts on that? I can't see anybody, so I'm not sure if I can.
Well, I think technology increases really quickly, and we like it's hard to predict that. So 2050, 2060, I think there's definitely a possibility that our technology would just skyrocket by then, but it's also possible that it won't.
Well, I actually agree with you. I think the ingenuity of humans to offset impending doom, they usually have to wait until it's impending, but then, yeah, I agree. I think technology will yeah, Clint.
I second the motion, and there is a tendency you will see in and various people usually who aren't technologically, aren't engineers or scientists or whatever, to believe that all the knowledge, human knowledge, all the technical knowledge that we'll ever have, we already have.
Yeah. Yeah.
And they're not people that have looked at the history of technology at all. Apparently, they were busy learning Greek and Latin or something.
Or geology. Yeah. Yeah. Thanks, Cliff. That's excellent. Okay, what about recycling of critical metals? So the authors discuss the need for recycling, but they do seem skeptical that this will achieve what is needed for a green economy. And so they have this figure here in the textbook showing these graveyards of, in the top, wind turbines, and in the bottom, solar panels. But my sort of comeback to that is that I think needs must, and that technologies are being developed to allow recycling of these green materials, including batteries from electric cars and so forth. And there's a lot of money going into efforts to recycle critical metals from these greener technologies. So I think that goes along with the previous comment about technological advances. And then I also would suggest that the need for critical materials, as it becomes more widely accepted, then companies will be encouraged, forced, or incentivized to change how they build things to allow them to be more recyclable. So, one example, I'm sitting here on a Macintosh computer. Apple doesn't make their computers out of plastic. They make them out of aluminum, which is highly recyclable. Just as one example. Okay. Yeah, not very nice looking images, but maybe one can argue those are potential ore deposits if we can figure out how to recycle them. So then they talk about the development of a circular economy. So there's a need to transition away from a throwaway culture to one that embraces the circular economy. And why? Because the Earth has finite resources, and it's getting more difficult to find large deposits. So recycling is more energy efficient than mining, and processing recycled material is more efficient on average than processing ore. And so as we have to go deeper to lower grade deposits, that requires more energy use, both because it's deeper and because we need to process more rock to extract the metals of interest. And again, maybe we can design products that are more readily recycled. So the little box there says that 26 million tons, I gotta get this out of the way, of copper are used globally, and between 2009 and 2018, and 32% was from recycling. And the nice thing about metals like aluminum and copper is you can continuously recycle them. They don't lose integrity through the recycling process the way that plastics or paper does. And then the authors make a really curious suggestion that if we don't figure things out, we're going to regress to this Iron Age, which seems pretty dire. But that's their opinion. I suspect we'll either figure it out technologically or we'll wipe ourselves out.
Well, so I think what he misses is the fact that as things get more expensive, fewer people can afford them. But there's always a way to make it economically
yes,
possible to make something.
Yeah.
And there will be a group of people that will be able to afford it. The challenge is that just like with oil and gas, we're never going to run out of those things. What we're going to run out of stuff is the stuff that the average person can afford. That's what we're in danger of running out of.
Right.
I think that though there's a secondary problem, right? That if you have this huge reduction in demand because most people can't afford it, then you have a reduction in the number of people who kind of know how to do something. And eventually, I suspect we will lose that expertise if you only have one or two people who can afford to buy it, and then you no longer have knowledge transfer.
Yeah, yeah, that's an interesting point. I mean, if we take a step back and look at the broader picture, if we look at automation and AI and loss of jobs and things like that, we're eventually going to have to rethink how we organize our society. Um, and maybe this is part and parcel of that. Okay. Uh, okay, so here's just the the figure they have in the textbook for circular economy was rather complicated. This one looks complicated, but it's kind of in two wheels. So the left-hand wheel is the sort of mining part of it. So we start with prospecting, we go to exploration and development, and we extract the ores, process and produce, close the mines, reclaim the land, and start prospecting again. And then from processing and production, we go to manufacturing, distribution, consumption, collection of the end-of-life products, recycle, design new things, remanufacture, and so forth. So, circular economy. Okay, future trends in mineral exploration. The quote is, "It is considered that uptake of a circular economy involving economically viable recycling of critical metals will be slow unless global governments become aware of the looming problems of metal depletion within an environment of, my emphasis, media-stirred hysteria concerning the catastrophic effects of climate change. Immediately improved success in mineral exploration for critical metals will be essential to the interim metal supply gap, given the currently long periods up to 20 years between deposit discovery and metal production." So we can discuss that. I mean, I'm not convinced that the media has stirred hysteria around climate change. I think they've reported what the IPCC and various other people have said, but that's just my opinion. What do people think?
Well, I'll comment on this. So
Yeah.
there was no reason to bring in media stirred hysteria concerning climate change. The point they made, except for that, is sound. It's just they've muddied the water
Mhm.
by putting this other thing in there. The two
Yeah.
are unrelated, right?
That's true.
They're
That's true.
related, but they're unrelated.
Yeah.
Whether we move towards a green economy or don't, we're still going to have the problem with metals.
Yes, that's true. Although, I mean, I guess what they would argue is that our need for critical metals will be less if we don't move to a green economy, right? Because
Right.
really
Yeah.
the demand for critical metals is being driven by the increasing electrification and solar power and wind power and so forth.
No, but the point about recycling, this is obviously the direction we want to go into.
Yeah.
But all of these initiatives are fundamentally tied to the economics, right?
Yes.
If the price for whatever you're recycling isn't more than whatever it costs to get that out, then nobody's going to do it. The only thing governments can do is put subsidies and tax breaks to encourage that activity. That is something that could be done relatively easily.
Yeah.
And we're seeing renewed interest in mines and minerals now. It's incoherent and it's caught up with a lot of other aspects of the U.S. administration's less helpful policies. But it's definitely there, and we're just going to have to watch and see how that evolves.
Yep. Agreed. Okay, we'll move on. So they described three advances in technologies that could radically change mineral exploration industry. So one is the adoption of drones that can carry sensors and even be used for sample collections. So the image on the right is from field work that I did this summer. So that's a drone being used to sample treetops, the branches from treetops for biogeochemical mineral exploration, just as an example. And I have a colleague that's been using drones to collect water samples without human interaction. Then the other one is mineral prospectivity modeling. So integration of lots of disparate forms of data to produce 3D, 4D models of ore deposits and exploration for ore deposits. And then they note the use of machine learning and artificial intelligence. That we get increasingly large data sets, it becomes harder and harder for humans to interrogate those data sets, and AI, that's where AI can come in. And then I would add robotics. I mean, increasing use of robotics in mining and mineral exploration. So in some mines, the ore excavating trucks are robotically operated. There's a new deposit being mined in South Africa that I worked on. It's deep underground and it's mostly being mined by robotics. Okay, so then they said, in summary, geology is a field-based. Oh, Madison.
I was just wondering if you could expand a little bit on the models currently being used, and if you know sort of what are the limitations, and are there particular minerals they're good for, or regions and conditions, or do they kind of like all have the same general error margins?
Sorry, I misunderstood. You mean models as in mineral prospectivity models?
Yeah.
Yeah. That's a great question. I think you can design them for any commodity type. I'm not a mineral prospectivity modeler because I'm a bit of a Luddite and it's hard for me to integrate large data sets. But I'm involved in a project where that's the ultimate goal of the data we're collecting, is to build a prospectivity model for different commodity types to guide exploration. In particular, to guide exploration under deep cover. About all I can say on that.
Okay, cool. Thank you.
Yeah. So then they say in the chapter summarizes that geology is a field-based science, and despite rapid technological advances, successful exploration geologists should keep an open mind, think creatively, and spend sufficient time in the field in order to base their decisions on the geological key observations that can only be taken on the ground. I've got no argument with that. And so the image is just showing Sarah, who's here on this course, sampling trees with a couple of colleagues in the forests of Finland over a VMS deposit. So yeah, we still need field work. That's one of the great things about being a geologist, going into the field.
I think I collected resin sample at that time.
Yeah, you were collecting resin samples. That's right. Yeah.